Last week, do you remember what we talked about last week? Does anyone remember?
Yes.
What did we talk about last week?
We talked about a bit of relativity and we talked about
Frames of reference.
yeah.
Frames of reference, yeah. Okay. So we're gonna talk about oh, I got to grab one more thing. So what I'm going to do today is we're going to talk a little bit more about frames of reference, and I'm going to ask you guys some quiz questions. I'm going to show you some videos, and then if we have time, hopefully we're going to get into planetary motion. Okay, hi Courtney. All right, so let's ask you a few quiz questions. I'm going to share my screen. I'm going to do the whiteboard, and hopefully this will work. Okay, is this working? Good. All right. Here's my quiz question for you. If I'm in a car and I'm going down the highway at 60 miles an hour, and I'm not accelerating, I'm not changing my speed, I'm also not changing my velocity by going around a corner, and I stand here in the car and I drop a ball, what's going to happen to that ball? Someone unmute and tell me.
It's just gonna go back up to you.
Are you saying like if it bounces or something?
Yeah.
Yeah, so is it going to go before it bounces, or let's say I just hold my hand here and I'm going to catch it. Is it going to go straight down or is it going to go way back? Jonathan, you have your hand up. What do you think?
Once it's not like connected with the car, once it's not in the car, so it's traveling.
No, it's in the car. I'm inside the car. I'm dropping it like this.
Yeah, what I'm saying is once you drop it, it's no longer going with the speed of the car, so it'll seem like it'll fly behind you when it's really is dropping from where you dropped it.
Okay, but I'm inside the car. The ball is inside the car the whole time.
Oh, then
And the
it'll just
windows are
stay where
closed.
you are.
Okay, right. Okay, good. So I'm inside the car. The windows are all closed. I drop the ball. It's going to fall straight down. Like I said last week, I'm not accelerating. My frame of reference is not accelerating. I therefore have the right to say I'm motionless, and it's the earth and the freeway and the trees that are going backwards at 60 miles an hour. Okay. So now I'm going to ask Jonathan specifically a question because I think he sort of misunderstood what I was saying. And now this time I think he'll get it right because I think he will understand what I'm saying. What happens if I stick my hand out the window, right? So my hand's out the window and I drop the ball, okay? Jonathan, answer the question because that's what I think you thought I was saying.
That's when it'll fly behind you.
Okay. Here's my question. And not Jonathan, but somebody else, just chime in because I can't, when I'm using the whiteboard, I can't see everyone's faces. So just unmute yourself and tell, why is that? Why does it go flying backwards?
Because anything in motion stays in motion. Okay.
So the ball was moving at 60 miles an hour relative to the earth, right? And then I drop it. So why is it going backwards? This is, remember, I'm sticking my hand outside the window. Courtney, do you know? So I stick the window and I let go of the ball, it's going to fly backwards. Whereas when I was inside the car, I dropped it and it went straight down.
Oh, because in the car it's going at a constant speed, but when it goes out the window, it's not going at a constant speed.
Okay. So true, but why is it not going at a constant speed? Anybody else want to throw out an, I can't see all your pictures, so if you're raising your hand, I can't tell, so just chime in.
Air resistance?
Oh, sorry.
Oh, okay,
Okay.
air resistance. Okay, so when I'm inside the car with the window closed and I drop the ball, it's going to fall straight down. I could pour a can of soda, it's going to fall straight down, just like it would if you were sitting at home. When I stick my hand outside the window and let go of the ball, it's going to go flying backwards, and that's because of air resistance. Now, let's for a second, let's try to keep our focus on the car as our frame of reference, okay? The car is going 60 miles an hour, but I have the right to say, I'm not accelerating, therefore, my frame of reference is perfectly valid. And yet when I stick my hand out the window, it goes backwards. And you know, we know that the answer is air resistance, but I'm gonna throw out a scenario. I want you guys to focus on the car as the frame of reference. The laws of physics work the same when I'm in the car as long as I'm not accelerating. Okay, so I stick my hand outside the window and I feel something on my arm. What am I feeling?
Air.
Air. I'm feeling the air go by. Remember, I have the right to say I am motionless. The air is going backwards at 60 miles an hour. The ground is going backwards at 60 miles an hour. The trees are going backwards at 60 miles an hour. I have the right to say that. So when I stick my hand outside the window, it's exactly the same as if my car was motionless and there was a 60-mile-an-hour wind going backwards. And what do you think would happen if I stuck my hand out the window and there was of a motionless car, motionless relative to the earth, but there was a 60-mile-an-hour wind, and I let go of the ball in that 60-mile-an-hour wind? What do you think would happen?
It'd fly back.
It would fly back. That's why the ball flies back. Okay, and so yes, from the ground, you can say, well, that ball is moving 60 miles an hour through the motionless air. So that person can say that. He says, oh, I'm on the ground, I'm motionless. The car is the thing that's moving. The air is motionless relative to me. Okay, he has the right to say that. And he says, well, it's air resistance because, you know, that ball is moving 60 miles an hour through the air, and the air, you know, provides some friction and slows down that ball. But from the guy in the car, he has the right to say, no, that's not what's happening at all. It's that I'm motionless and there's a 60-mile-an-hour wind going backwards. And that's why when I drop the ball, it goes backwards. So, you know, this was a hard thing for people to figure out. It didn't happen until 1600, okay, with Galileo, when he realized this whole key concept of frames of references. Okay, we're going to take another one. So we talked about, let's see here. We talked about the swimmer in the water. Welcome to whoever's coming. I can't really. So here's water. The water is moving 2 miles an hour to the right. And we have a swimmer who is actively swimming. So here's his arms. I'm a terrible artist, but here's his arms. His arms are doing this. His legs are kicking, kick, 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 kick. He's not happy. He's frowning because he's trying so hard, but he is going 2 miles an hour upstream relative to the water. This guy right here, what does this guy say the swimmer is doing relative to this guy? How is the swimmer moving? Is he moving to the left, the right, or staying the same? Someone chime in.
He's motionless. He's the same spot.
Exactly, because the water's moving 2 miles an hour to the right. The swimmer's relative to that water. Swimmer's moving 2 miles an hour to the left. So by the Galilean transformation, you have a positive 2 minus 2 equals 0. He sees this guy motionless. Okay, here's another question. I have a car. Let's say it's a truck. Here's the truck. In the back of the truck, there is a cannon, just like me.
Yes.
There's a ball inside the cannon. The truck is going 60 miles an hour to the left, and this cannon is calibrated to shoot the ball 60 miles an hour to the right, relative to the cannon. Relative to someone on the ground, what's that ball going to do once it leaves the cannon? How fast is it going to be moving?
It stays still, right?
It's going to be going 0 miles an hour, exactly. Now, has anyone ever watched the show Mythbusters?
No.
Okay, Courtney has, and probably some other people out there have too. I just can't see everyone's faces. There's a show called Mythbusters, and it's run by a couple of guys who do stunts. That's what their previous occupation was, is they did stunts. I got to tell you, they're not very good at physics. But what they do is they take these myths or things that people claim that don't seem like they should be right, and then they try to. They're very good mechanically, and then they try to figure out a way to mechanically answer the question. Okay, so they did this exact experiment. They put a truck and they loaded. It wasn't really a cannon, but it was something that it could shoot a ball, and that they could precisely tune the speed, the velocity of the ball when it left the cannon, so that it was precisely the same speed that the car was going. So the car's going to the left, this cannon shoots the ball, and it's calibrated to make the ball exit at exactly the same speed that the car is going. Now, it's a 60-minute show, and they probably spend 30 minutes trying to show how they made this calibration, because it's, you could imagine this is really hard. I wouldn't even have the slightest idea how to do it, because I'm good at physics. I'm not as good at mechanical things. What we're going to do is we're going to watch a movie of exactly how that worked. So hold on for a second. Of this experiment. So it's going to be kind of shortened because we don't want to watch the whole thing while they do the calibration. We want to watch what happens. Oh, shoot. Let's see. What we want to watch is we want to watch what happens when they do this experiment. Now, in the two videos I'm going to show from Mythbusters, I got to tell you, it's kind of funny because they act like, ooh, physics, ooh. It's kind of funny. It's just that's not their field of expertise. They're mechanical guys, right? So it is kind of funny to listen to them acting like this is like some amazing thing that they've just proven, even though, Galileo said it 400 years ago. Okay, can everyone see a picture of a woman on the screen?
Sure.
Yes.
Okay, here we go.
You can't hear it.
Did you
Can't hear it.
share
Okay.
your sound?
Okay, you can't hear it. Is that what
You
I
need
heard
to
someone
share
say?
your Sound.
No sound?
Yeah,
Yeah.
you need.
Okay, so I got to enable sound. How do I do that? Cancel that.
Well, do you really need it?
Yes, you do, because it's fun to listen to them ooh and ah about the physics of it all. So I'm going to just stop sharing, and then I'm going to share screen. Let me just see this. Advanced sharing options. Share screen. This one, and then, share computer sound. How's that? Optimize screen sharing for video clip. We'll try that. Okay. Let's holler if you don't get this.
Feeling that we are very close to a perfect demonstration.
Good.
We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air. It stops and it just falls.
Look at that. Fantastic. I mean, look, it doesn't move at all. It's going straight down. Dude.
Woo! We did it! We did it! Yeah! Vector edition! Yay! We canceled out velocity!
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball. We got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
Look, Limu! Someone needs help customizing.
No!
Oh, you want to watch the emu commercial?
Jackson would love it.
Okay. All right. All right. Okay, we're going to do one more. We're going to do one more thought experiment. Okay. So now I want to go to the whiteboard again. Going to erase all this garbage. I have a gun. The gun is going to shoot a bullet with a velocity to the right. Does anyone just throw out a number how fast a bullet travels?
I heard once that was like sort of around the speed of sound, like that area.
Yeah, I think you're right. I think it's somewhere around the speed of sound. Obviously, it depends on which one it is. We were watching a video the other day. It was called like Slow Motion Guys, or I don't know, Jonathan or Alyssa, can you remember what it was?
Guys.
Slow-mo guys?
Yeah, it was slow-mo, guys.
Anyways, so they had this like big giant artillery cannon, the biggest artillery in the world. And I remember they said something like 1,200 miles an hour, which is about twice the speed of sound. But I suspect that for a bullet, we're just going to say it goes a little bit less than the speed of sound, 600 miles per hour, that way, relative to the gun. Now, does gravity still work on that bullet?
Yes.
Yes. Okay. Do you think that ball is eventually going to hit the ground?
Yes.
Yeah. Okay.
See
Here's
where
my
this
question.
is going.
Okay. I have a bullet that I'm not shooting, but I simply drop it, and it's going to go straight down. If I drop the bullet at the exact moment that I shoot this bullet, which one will hit the ground first?
Can I say?
Sure.
They'll hit at the same time.
Well, that's a good guess, and it happens to be right. Okay, so let's think about this in frames of reference, okay? Let's say that let's first consider this bullet from this guy's frame of reference. He's fixed on the ground, he's not accelerating. He watches the bullet drop, okay? And it takes a certain amount of time to drop. Let's say it's a quarter second. You know, it's actually pretty easy to figure out if we know how high the bullet is being dropped from, but I don't want to take the time to do that because that's not what we're learning about today. And everyone can see my whiteboard, right?
Yes.
Okay. Now let's consider a different frame of reference. This frame of reference consists of a box and a guy standing in the box, and the box is going 600 miles per hour to the right, okay? He's not accelerating, he's not changing his speed or his direction. The laws of physics apply to him equally as they do to this guy who's on the ground. What does he see when he looks at this bullet? Well, how fast is this bullet moving relative to him?
It's not moving.
It's not moving. His box is moving along, you know, relative to the ground, 600 miles an hour to the right. The bullet is moving relative to the ground, 600 miles to the right. He sees this bullet as being motionless. So while the person on the ground sees that bullet flying through the air, he does not. he sees it as being motionless. And what happens when you drop a motionless bullet?
It drops.
It drops straight down. These bullets will hit the ground at exactly the same time. Now, the fact of the matter is that there is some air resistance, and you know, maybe the bullet is rifled in such a way that, you know, it doesn't, you know, I don't know, like there's some air forces on it, or, you know, maybe the air is pushing it down or lifting it up. I don't know. But for the most part, a bullet that's shot at 600 miles an hour, perfectly level, as long as it's perfectly level, will fall at the same speed as one that's motionless. So now what we're going to do is we're going to come back to the Mythbusters again and watch another video of them. Demonstrating this exact thing.
Can we watch the emu commercial? It's only 5 seconds long.
No, no emus for you. For you.
What you got there?
This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no limbs.
Do you kind of get what I mean when he's like, based on what theory? Like this is like basic physics, right? This is like stuff he should have learned in high school, but that's not their area of expertise. And they would make fun of me if I tried to do something mechanical like what they're going to do, but I just think it's funny.
Lift. Thus, gravity has the same effect on it as it does on a drop bullet, and thus they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6.
Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24 of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24 of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
Okay, so who would have guessed that that's what would have happened a few weeks ago? Did everyone already know that, or does that seem kind of like you wouldn't have thought that?
You taught that to me before.
Okay, fair enough. Anyways, I think that's kind of cool. I still get a kick out of them saying, physics first, no, people have known this for like 400 years. But
The
anyway.
best part was when he was like pretending to be like, and then divide by this and this
Yeah.
and multiply.
Yeah, it was funny. Okay, so let's now, we're gonna step away from frames of references for a few minutes, and we're gonna do something else. We're gonna talk about planetary motion. Now remember, the reason why we came to frames of reference was because people, had nothing to do at night 1,000 years ago, and so they looked at the stars, right? And they were much more observant about what was going on in the heavens than we are, because there was nothing else to distract them. So you guys all know that the sun rises in the east, goes across the sky, sets in the west, right? And hopefully, if you haven't already, someday you'll go out at night. It's easier in the winter because the nights are, it gets dark earlier, but, if your bedtime's after 10 o'clock, you can certainly see that now. And you'll notice that if you put your eye on a certain star, you'll notice that it goes across the sky from east to west, okay? I mean, that's something that people have known for thousands of years. So again, the reason why we got into frames of references is because people said, I don't feel myself moving, I can't be moving, it must be the stars and the sun and everything that's going around us. We have to be at the center of the universe, everything has to revolve around us. And Copernicus in the 1500s said, no, this would make so much more sense if everything went around the sun. I can't explain why we don't feel motion, but it would make so much more sense. Okay, so we're going to talk a little bit about motions of planets. Okay, so here's what I'm going to do. I'm going to share screen. Oops. Let me go back to this.
Once me and my dad went camping, like way out, and our tent had a mesh on the top so we could see the stars, and we stayed up and just watched it. We watched the whole, everything just move, and it Earth was moving, not the stars to me.
Yeah, who's talking? I can't really see right now, but who's talking?
Jackson. Alan.
Jackson. Okay, cool. Yeah, awesome. Well, that's exactly what we're going to show. So excellent that you've already seen that with your own eyeballs. This is time-lapse photography, and in a little bit, these people will be out of the way. This is night sky, stars moving from east to west. So that's exactly what the sun does. It moves from east to west, right? Now I'm going to show you a little bit different video. And this one is going to look a little different. Now I happen to know, because I know enough about astronomy to say so, I happen to know that that shot was pointed south. Those mountains that you saw were pointed south. And I know that because they were mostly moving from east to west. I'm going to show you another picture, another movie. This is time-lapse photography pointed north. And you might say, how the heck can you tell which direction you're pointed just by looking at the video? I think you'll see a big difference. What do you notice about these stars? They're moving left to right?
They're revolving.
They're revolving. These ones are going up. These ones over here are moving down. These ones are moving to the right. These ones are moving to the left. They're revolving in a circle. Now, I don't like what they're doing here. What they've done is, instead of doing time-lapse going forward, they've done a time-lapse in reverse where they're having an open exposure of a camera so that you can actually see the trails of the stars. In other words, what happens is they leave the camera taking the same picture for long enough that it shows where the stars have been as well. Now you'll notice that this time the stars are going counterclockwise. Well, unfortunately, that's because they ran this backwards, and I can't for the life of me think of why they did that. It's just confusing. But you can see but the stars are going around a circle. And is there a central point to this circle?
Yes.
Yeah, it's the North Star, huh?
It's the North Star, exactly. Now that star's official name is Polaris. And does the whole sky revolve around Polaris? I mean, that's an unclear question. I mean,
No.
you could say, well, gee, there's something special about Polaris. There's absolutely nothing special about Polaris. Polaris happens to be a bright star that happens to be directly above the Earth's North Pole at this time. And so it appears as though all the stars are moving around it, but that's just coincidence. I mean, in the southern hemisphere, when they look south, they see the same thing. They see the stars all moving around the central spot, but by coincidence, there's not a bright star right there above the South Pole. And so they don't get the nice navigational tool that, you know, people, sailors and stuff had in the northern hemisphere, where they had something that, at night, they could always tell which direction was north just by looking at that star. So I'm going to run this for a little bit longer so you can see some more of it. And I think you can see that the North Star is a little off center. I make it that the center is right about here. And here's just a little fun factoid. I don't know if you guys have ever played with tops, but if you spin a top, it doesn't just spin around, it kind of goes around in a circle. And actually the Earth, it's called precession, and the Earth does that as well. It's not worth explaining what precession is, other than the fact that I can tell you that in another 1,000 years or 2,000 years, the North Star will no longer be very close to the North Pole. As the Earth precesses, there's a different star there's a different part of the sky that's going to be directly above our North Pole. And so in the times of, back in the Egyptians' time, this star Polaris did not coincide with the exact North Pole. It was probably more out this way. So we're fortunate that we live in a time where that Polaris is pretty close, and it's a bright star, and it's real nice. So that's what happens over the course of the night, okay? But what we want to talk about now for a couple more minutes is not what happens over the course of the night. We want to talk about what happens over the course of a year, okay? So to explain that, I'm going to do something first. I'm going to show you guys a video. Let me stop sharing this. I shot this video out of a car window. Whoops. Let's see, share screen. This one. Okay, there's about 4 seconds here of video. I want you to watch this. Okay, so my car is going down the freeway at 60 miles an hour. Now, what do you notice? Compare the trees to the hill in the background. What do you notice?
It looks like the hill is moving slower because it's farther away.
So it looks like the trees are moving fast. It looks like the hill is moving slow. Okay? Now, relative to me, I'm in a car, I'm moving at 60 miles an hour. Both of them are moving at the same speed. But Jonathan said it looks like the hill is moving slower because it's farther away. And that's absolutely right. I mean, you can look at it this way. If I'm moving 60 miles an hour, then in 1 minute I move a mile, and in 1 second I move a 60th of a mile, okay? A 60th of a mile is a long ways when you're talking about trees that are, let's say for fun that there's 6,000 feet in a mile. It's a little bit less than that. But so that means in 1 second, I'm gonna travel 100 feet. And so for a tree that's 20 feet away from me, if I've moved to the right 100 feet, that's a long way. But a hill that's maybe 3 miles away from me, moving 100 feet doesn't make all that much a difference, okay? And you can prove that to yourself. I want everyone to do an experiment. I want you to put your finger right in front of your nose, okay? And then what I want you to do is I want you to alternately close one eye and then the other. Oh, I forgot to say something. Put it in front of your nose in such a way that you can see the wall behind you. So you don't want, like for me, I don't want it in front down here because that's in front of my computer screen. I want you to be so that when you close your eye one at a time, go back and forth, what do you see happening to the finger relative to the wall behind it?
Seems like it's moving, because
it seems like it's moving, right?
Your
so what's
eyes.
going on is that your eyes are, let's say your eyes are 3 inches apart, and you've got a finger that's 3 inches in front of them. When you move your perspective right to left 3 inches, that's a pretty big difference relative to your finger, which is only 3 inches away. But relative to the wall, which is maybe 10 or 15 feet away, depending on how big your room is, moving your eye, your point of view 3 inches is not a big deal. So it doesn't appear to move. This illustrates a physics principle called parallax. And what it means is that when you change your point of view, things that are close will seem to move quite a bit, and things that are far will seem to move not much at all. Okay, you can actually, with a little bit of geometry, you can actually use this principle to determine distances. So for example, when people first wanted to measure the distance to the moon, what they did is they would put telescopes, like say in London and Paris, and they'd measure the distance to the moon. They'd measure the angle to the moon. They take into account the curvature of the Earth. And then they would say, okay, well, relative to the guy in London, it's at 37 degrees, and compared to the guy in Paris, it's 36 degrees. And they would have to do a lot of geometry because, you know, the Earth is round, but they could easily figure out the distance to the moon, okay? Just by the way it changes its apparent position relative to the background stars. The stars are really far away, really, really, really far away, like incomprehensibly far away. And so that doesn't really work when we're talking about stars. You can't like set up a telescope, you know, a few hundred miles away and expect to see much difference. But the way that they first measured the distance to the stars is they would say, well, let's measure where a star is in January, and then 6 months later we'll be on the opposite side of the solar system. So it's 93 million miles to the sun. We'll be another 93 million miles to the other side of the sun. That's 186 million miles. That's a big difference, and maybe that will be enough to give us, you know, we can with parallax figure out where the how far away the stars are. And people were, with the nearest stars, they were able to figure out how far away those stars are. And that's how the people first got the distance to the stars and realized, oh my gosh, this is a huge, huge distance. So we're coming up on 45 minutes, and I'm trying to keep these to 45 minutes. So what I'm gonna do is I'm gonna just, since we just finished talking about this thing with parallax, I'm gonna show you part of the video, but I'm not gonna show you the whole thing. Okay, so I'm gonna share, let me go to here, and then we'll pick this up again. We'll pick this up again next week. So we're talking now about the planets and how they move relative to the background stars.
In the night sky, stars rise and set due to the rotation of Earth. However, the pattern of stars that is seen in the sky, how far apart a pair of stars are seen from each other, stays the same over timescales of thousands of years. However, planets move in the sky.
Now, that's despite the fact the stars are in fact moving, right? They're rotating around the, or they're revolving around the center of the Milky Way galaxy. But because they're so far away, even though they're moving fast, they're moving really fast, you can't really see them move even over a period of thousands of years. So that's very similar to the hills as I was in my car. They don't seem like they move all that much.
Sky relative to the pattern of background stars. They change their position in the sky from night to night. The term planet originates from the Greek word for wanderer. This phenomenon can't really be seen on any given night, but if you note the location of a planet relative to the background stars, and note its location again several nights later, you will see that it has moved.
Okay, so again, we're not talking about what you can see on a given night. The stars move from east to west, just as we've described, and so do the planets. But over a longer period of time, if you watch the position of the planets relative to the background stars over a period of days and weeks and months, you will see that they in fact move.
This could be seen if you took a series of photos every night for a month with a chosen star highest in the sky and laid them over the top of each other. Planets typically move eastward, the direction of increasing right ascension, which we know today is due to their revolution around the sun. Note that a planet still rises in the east and sets in the west on any given night due to the rotation of Earth. This video will focus on a variation of that motion known as retrograde motion.
Okay, and it happens that, so there's all the planets move eastward, and the reason for that is that when the solar system was formed, basically it was a swirling cloud of dust, and as these planets formed, they all were going around in the star in the same direction. And every planet that they've observed in other solar systems do the exact same thing. They maybe have noticed one or two that are going in different directions than the rest of the solar system. But generally speaking, planets form from a swirling cloud of dust that's going in the same direction the whole time. And so that's why planets always go around the star in the same direction.
This apparent motion concerns the planet slowing in its eastward motion, stopping, moving westward for a while, and stopping again before continuing on its eastward journey.
Okay, so the Greeks, they knew this, and they had to figure out what the heck is going on here. Why do these planets generally move eastward? It would make sense if they always moved eastward, over the course of days to weeks to months, if they were rotating around the Earth. But how do you explain the fact that in the middle of their eastward movement, again, over the course of weeks and months, they suddenly stop and go backwards? How do you explain that? So we're going to look at, there was a guy named Aristotle, and he had a student named Ptolemy. Aristotle first came up with this explanation, and then his student Ptolemy, who also worked at the library at Alexandria in Egypt, he refined the system more. And we're going to talk about how they explain this, and then we're going to stop and we're going to watch the rest of this video next week and talk about the real explanation.
Superior planets, those that orbit the sun further out than Earth, and the only planets that will be discussed in this video, this effectively creates a loop in the sky. 2,000 years ago, the Greek astronomer Ptolemy explained retrograde motion with a geocentric system of wheels within wheels, kind of like the kids' drawing game Spirograph. It was believed that Earth was at the center of everything and that a planet moved on a circular path called an epicycle, the center of which moved on.
Okay, so you guys, I want you to look at my arrow. So here's the Earth, we're motionless, we're at the center of the universe. We see a planet is going around eastward, and then right here it slows, and for a short time it goes westward before continuing its eastward journey. And so the Greeks believed that a circle was a perfect object. So they were convinced, and for a long time people were convinced, that the planets had to move in a circular motion. So he said, well, clearly if they just go around in a circle, that doesn't make any sense. They're going to go around a circle, right? But he said, well, what if there's a circle on a circle? So he imagined, Aristotle and Ptolemy imagined what they called crystalline spheres. So imagine a glass sphere that surrounds the Earth. And as the sphere rotates, okay, then moves the planets eastward. But in that sphere, in that crystalline sphere, there's another crystalline sphere, and it is also rotating. And so even though you know, the first sphere is moving east to west, like this, west to east. The other sphere is moving this way, and so every once in a while you see, mostly it's moving from west to east, but every once in a while this other sphere moves it from east to west. And unfortunately, that didn't explain things very well. And so Ptolemy, who revised this theory of Aristotle's, by the end of his life, he had created 54 crystalline spheres that explained the movement of the 5 planets. He had so many spheres on top of spheres on top of spheres. They're all crystalline. You can't see the spheres. All you can see is the planets that are on the spheres. Okay. It was really unworkable, and it didn't even do a very good job. It was okay, but it didn't do a great job. Copernicus in the 1500s hated this. He said, this is absolutely ridiculous. This is so complicated. You know, nature is simple. When you figure out the rules, nature is simple. That's what Copernicus said. So he said, I don't know how to explain why we don't feel the motion of the Earth, but it would be so much more fit, so much better if the planets moved around the sun, and then we wouldn't have to have these 54 crystalline spheres. And he worked out why planets would appear to move backwards relative to the background stars if you had a sun-centered model of the universe. And that, my friends, is where we're going to pick up next week. Okay, we'll talk about how putting the sun at the center of the universe explains why planets move backwards. Okay. All right, guys, good to see you. Yes, Lissa.
Wait, so just to make sure, does my Chromebook, can you hear me all right?
I can.
I want to use this one.
Did you have a question, or you just wanted to see?
I just wanted to see.
Okay. All right, guys, talk to you later. See, I'll let you know when we are going to meet next week, okay?
Thanks, Dad.
All right, talk to you later. Bye.
Bye.
Goodbye. See you in light.
Okay.